First of all, I would like to thank the organizers for inviting me to this very nice atmosphere and this conference as well. So I could make it a little bit late, but at least I could arrive for half of the second half of the meeting. So I will talk about particle acceleration by reconnection and the associated products like gamma ray and neutrino emission around in the vicinities of black holes and relativistic jets. And this is work in collaboration. This part of my project is a work in collaboration with these people. Most of them are postdocs and students in my group, and some of them are in here, like Luis Cadovac, who talked yesterday, and Juan Carlos Rodriguez Ramirez, who will talk right after me. And also senior collaborators like Yuzuki Mizuno, Gene Stone, and Greg Koval, etc. Okay, so let's start talking about what is reconnection. Okay, when we have the approach of two magnetic fluxes of opposite polarity in an environment with a finite resistivity, electric resistivity, it has to be only tiny one. Then in this case, these two fluxes will reconnect, which means that they are going to annihilate partially at the point where the fluxes of opposite polarity meet, and then it will build a new magnetic field topology. And of course, this implies the non-conservative release of magnetic energy, right? At the interface where this encounter occurs, this magnetic discontinuity, we can see that the charge current density J that is given by, in a magnetohydrodynamical flow, it is given by the curl of B of the magnetic field. So the charge density, the current density J, is simply given by 2bc over c divided by delta, where delta is, the thickness of this magnetic discontinuity. And because it's very small, this implies that the current density J is very large. And that's why we call these magnetic discontinuities as current sheets, right? So this kind of phenomena is directly observed in the Earth magnetotail and also in solar corona, in events of solar flares. These are direct observed reconnection, but in these events, reconnection is flaring, is fast, which means that the reconnection velocity is of the order of the alpha velocity in this environment, right? So, this is essentially what we know about reconnection in the solar system, but we know that now reconnection is regarded as important also beyond the solar system. Nowadays, there are several studies of reconnection in systems like star-forming regions, the pulsars, the pulsar wind nebulae, accreting neutron stars, relativistic jets associated with AGNs and GRBs, and of course stellar X-ray flares associated to other stars than the sun, and also in accretion disk phenomena. For instance, in star formation, reconnection, fast reconnection has been recognized as a key mechanism to remove excess of magnetic flux from star-forming systems to allow the final collapse of the stars. And in these other systems, reconnection is invoked in order to explain mostly high energy phenomena, as we are going to explore in this talk. In this talk, we have been exploring reconnection, violent reconnection phenomena in all these sorts of systems, but I will focus in this talk on reconnection around relativistic jets and black holes. So, this talk, I will show or try to show you that magnetic reconnection can be a very powerful process to accelerate particles, relativistic particles. Also provides an efficient conversion of magnetic into kinetic energy, and finally may explain very high energy and neutrino emission around black holes and relativistic jets, at least in regions that are magnetically dominated, solving current puzzles in the literature to explain these high energy phenomena, as I'm going to stress out in my talk. Let me start with a quick review on magnetic reconnection and its connection with particle acceleration. First of all, okay, we have seen what magnetic reconnection is, but the very first model proposed by, to explain magnetic reconnection was proposed by Eugene Parker and Sweet, and they assumed that the two fluxes of magnetic field lines with opposite polarity getting together, they would meet in a very large surface with an extension L of the size of the system, right? But if we use magnetic flux conservation equation, we can easily show that the reconnection velocity, the velocity at which these two flux stubs will reconnect, will encounter each other, will be of the order of the alpha velocity multiplied by the ratio between the thickness and the extension, right? Because we use flux conservation, so everything that gets in goes out somehow, right? And because of this relation, because delta is much smaller than L, this makes reconnection velocity very small. Or in other words, the process is too slow, too inefficient to explain, for instance, solar flares that are produced by fast reconnection. So we need a mechanism that produces fast reconnection. And then Pechek in '64, last century, he came about with this idea that in order to speed up reconnection, instead of making the lines to encounter in a large surface, they could meet essentially in a point or in a line, right? In 2 dimensions, it would be in a line. So that this makes L of the order of delta, and therefore you can see that the reconnection velocity is going to be finite, not anymore small, right? And as a matter of fact, they found out that it would be given by this relation, where S is the Lundquist number that gives the ratio between the dimension L times the alpha velocity divided by the electric resistivity. And even though this number is too large for most astrophysical systems that are very good electric conductors, this depends on log of S, and therefore Neperian log, therefore this is a finite. Nevertheless, in the 90s, Biscamp found out that this process would be unstable and quickly evolved to a Sweet-Parker slow reconnection, at least for MHD flows, unless we have pair plasmas at kinetic scales. So for collisionless kinetic plasmas, this mechanism prevails and can still explain fast reconnection with a localized resistivity. Nevertheless, okay, this made the community to think that fast reconnection would be possible only in kinetic plasmas, collisionless plasmas, and would prevail only at kinetic plasma scales. But until then, Lazarian and Vishniak, they proposed a process to make reconnection fast even in magnetohydrodynamical flows. And this occurs if we have turbulence. And turbulence is very ubiquitous in astrophysical plasmas. And why is that turbulence can make reconnection fast? As this was anticipated yesterday in Luis Cadovac's talk. In the presence of turbulence, magnetic field lines wander. And then we have reconnection, patches of reconnection occurring simultaneously in several points in our flow because of this wandering, this wrapping around of the magnetic lines. And all you need is just a tiny underlying resistivity, electric resistivity, like Spitzer resistivity. And they demonstrated that in this case, the reconnection velocity is given by this relation, where L again is the large scale dimension of the system, the alpha velocity, but the small l and VL here correspond to the L corresponds to the scale of the turbulence that can be of the order of L, the injection scale of the turbulence, and VL, the velocity of the turbulence at the injection. So we have something that is pretty fast. And besides, of course, because we have reconnection in turbulent flows, this automatically violates the frozen-in condition, the flux freezing condition, the alpha flux freezing condition in turbulent flows, right? Okay, so this has been tested successfully by means of three-dimensional MHD simulations. So reconnection is intrinsically a three-dimensional process. This has been tested by Koval and others. And here we have the current sheet, and showing that in the presence of turbulence, the current density gets, patchy, gets this complex structure. Okay, what is the connection of acceleration, particle acceleration with reconnection? Before stressing this, let me remind you that reconnection implies in release of magnetic energy, and this can be flaring in a flaring process. Huge amounts of magnetic energy can be released, as we see, for instance, in the solar corona, right? And it has been demonstrated by kinetic particle in cell simulations that about 30 to 40% of magnetic energy is converted into kinetic energy of particle of the flow, right, into particle motion. And laboratory plasma experiments of reconnection has shown that at least 50% of the released energy goes into particle motion as well. But how to accelerate particles in reconnection sites? Okay, this is the idea that we first proposed, Alex Lazarian, myself, we proposed this back in 2005 in analogy with first order Fermi shock acceleration. What happens within a shock? We know that particles trapped within the shock, superthermal particles, can go across the shock, and whenever they bounce back and forth and they go back to the upstream region, they undergo head-on collisions with the magnetic fluctuations, and at the end of a round trip, they end up with an average growth of energy that is proportional to the first power of the shock velocity divided by c. So this is the first Fermi order process that we know works quite well inside shock discontinuities, velocity discontinuities, but inspired by this process, we suggest that this could also occur inside magnetic discontinuities, because, the converging magnetic flows that come into the magnetic discontinuity, the current sheet, to reconnect, they also bring about plasma, and particles going back and forth between these two converging flows of opposite polarity will also suffer head-on collisions with magnetic fluctuations in the underlying plasma, and then they will undergo a first-order process where delta E over E is going to be the energy increment after each round trip will be also proportional to the first power, but now of the reconnection velocity divided by c. So we need fast reconnection in order to make this process efficient, right? Vrec must be of the order of the local Alphen speed. So this is the overall idea. Here is a cartoon that shows how particles would bounce back and forth and get energy increased, but we have also tested this numerically. So for instance, here we have a single test particle, and when it drifts and when it gets into the reconnecting the current sheet, they madly start to bounce back and forth, and then their energy increases exponentially as predicted by the first Fermi theory, as we predict in our treatment, and also their larval radius increases exponentially, right? So, but we have also tested this process in two-dimensional MHD simulations using also test particles in order to compare with the kinetic particle in cell simulations. So for instance, in this diagram, we have a two-dimensional simulation with several multiple current sheets built, and because of the underlying numerical resistivity, the current sheets get unstable to tearing mode, and they break quickly into islands or plasmons like these ones, magnetic islands. And because this is 2D, because in 3 dimensions, these magnetic islands will form like elongated flux tubs that arise perpendicularly from this screen, right? So these are nothing but, you know, the cross-section. Magnetic islands are nothing but the cross-section of flux tubs, magnetic flux tubs, right? But anyways, in these numerical tests, we demonstrated the equivalence between the two processes. The one that I have just described, where particle directly bounce back and forth within a given section of the current sheet, and also particles that are trapped inside these converging magnetic islands. They also undergo the same, you know, exponential acceleration in their energy and the exponential increase in their Larmor radius. So the process seems to be, once we have fast reconnection velocities, the process seems to be very efficient. But since we have proposed this first order idea, I mean, there has been a lot of development on the theory of particle acceleration by reconnection, mainly probed by numerical simulations. Most of them studied, investigated in particle in cell methods at kinetic plasma scales in 2 dimensions and 3 dimensions. But at those scales, we can probe only few plasma inertial length scales, 100 to 1000, where C over omega p here is the plasma frequency. And what about the larger scales of astrophysical systems like the surroundings of black holes and relativistic jets, etc.? These, and even diffuse media, these may require a collisional magnetohydrodynamical large-scale description, and this is what we have been doing, and other groups as well, using MHD simulations as a tool with particle launching test particles in these MHD environments of reconnection in order to study and understand better this process. So in the next few slides, I'm going to show you some of the results of these 3-dimensional MHD simulations, where we launched test particles within the current sheet with turbulence embedded already to make reconnection physically fast, naturally fast. So for instance, in green here, we do see the propagation of a test particle inside the current sheet. Here you can see in red and in blue the 2 magnetic fields projected on the walls of opposite polarity, forming this encounter in this current sheet, and inside the current sheet we have these patchy structures that are provided by the magnetic structures and the current density distribution, right? So essentially what we do, we follow the trajectories of the particles and how they are accelerated by the effective electric field provided by the magnetic fluctuations inside that are essentially V cross B term, right? Okay, so we do follow their trajectories, and for instance, in this sort of test, we injected 10,000 particles within this reconnection, 3-dimensional reconnection site. And here we have a diagram that shows the kinetic energy distribution of these test particles as a function of time. And we see that after an initial drift, when they reach the current sheet, the reconnection region, they do accelerate exponentially in this log-log diagram. This is an exponential growth in their energy with time as predicted by the theory. And their energy grows exponentially until a saturated condition that comes when the Larmor radius of the particles becomes bigger than the acceleration, the size of the accelerating zone. So, and what about the spectrum? Okay, we might expect, if it's a firm process, we might expect a power law development. And as a matter of fact, even though test particle is not an appropriate method to build a real spectrum, we see that shortly after, once the particles get into this region, a power law tail quickly develop with the power law indices that are in agreement with the peak simulations and also with what is expected from cosmic ray observations, power law indices between -1, -2 or something like that. So, and also we have tested, we have swept our parametric space of turbulence, both considering different parameters of the injected turbulence in the system and different reconnection velocities at injection in our turbulent current sheet, in order to see how these parameters would affect the results. And what we found out, we could extract directly from the simulations the dependence of the acceleration time by reconnection as a function of the energy of the particles, and we do see that we have this power law dependence that is pretty independent of the local parameters of the turbulence. And this is reasonable because this explains or shows that the reconnection acceleration process is independent of local parameters, in the sense that it's a pretty universal mechanism. So let's move on. These results are pretty general. They could be applied to any system where magnetically dominated or magnetized systems where we have we have, for instance, large-scale magnetic field lines with accompanied by with embedded turbulent magnetic field lines to make reconnection naturally fast. But in this talk, I will focus on the implications of these process into the surroundings of black holes and relativistic jets. So let me start with relativistic jets. So let's start with the relativistic jets. Okay, in the neighborhood of the region where these relativistic jets are produced, here for instance we have this cartoon that shows a supermassive black hole with a accretion disk and a relativistic AGN active galactic nuclei jet that could be a blazer if the jet points to the line of sight, to our line of sight, or a radio galaxy or safer galaxy, no problem, depending on the orientation of the line of sight with regard to the jet itself. But why to study the possibility of reconnection acceleration in relativistic jets? Okay, so I'm going to give you some observational motivations on how this mechanism can help to solve current puzzles, and then we will explore this more theoretically. So one of the motivations come from blazer jets. Jets that are relativistic, that point to the line of sight, whose emission is Doppler boosted, but some of these blazer jets, as for instance these sources, have been observed to produce TV flares, or in other words, emission with high variability, with variability of this time scale, a few hundred seconds. This implies that the acceleration region is really compact, and also in order to avoid the pair creation, electron-positron pair creation, by these gammas produced at these TV scales with this large variability, one has to invoke or assume that at least the emission zone would have Lorentz factors that are pretty large, larger than 50. But this is much larger than the bulk Lorentz factor that is expected for these blazer jets, right? Relativistic jets in blazers. And so this poses some very hard limit to explain how this is produced with the standard shock acceleration, for instance. And because it requires a very fast and extremely compact source, emitting zone. And as far as I know, the only successful acceleration model that has been able to explain such flares has been proposed by, as proposed by Janusz Uzdensk and collaborators, is reconnection. Reconnection in like a mini jet inside the jet itself, in which these constraints could be fulfilled, right? Also, reconnection has been invoked by Zhang and Yang in this very famous work in order to explain prompt gamma ray emission in GRBs. Essentially, the idea is that parcels of plasma would get piled, would be going downstream, and in the presence of turbulent reconnection, this process of prompt gamma ray emission would get very fast in this process. And another motivation perhaps comes with this new source that has been, you know, this famous release that we had a little more than 1 month ago in Science paper that announced the first simultaneous observation of neutrino emission and gamma ray flares in this TXS blazar source. And so we have this gamma flare associated with the observations of neutrinos by the ice cube. And you know, in order to produce at the same time neutrinos and gamma, probably we need very high energy cosmic rays with energies above those that are observed, of course, and these a natural process that could produce both of them is through proton-photon interactions, where we have both gamma and neutrinos, right? So the question that one might make is this: are these gamma flares and neutrinos in blazars produced by accelerated cosmic rays in the magnetically dominated regions of these blazars? And if so, would reconnection prevail as the acceleration process? So in order to try to explore a bit more these questions, I'd like to emphasize that so far the mechanisms that we know that may produce jets, the best mechanisms are as proposed by Blandford and Payne and Blandford-Znajek. In either mechanism that you guys at this time in this conference you might know quite well how they both work, but you know, in both mechanisms magnetic fields are required, and we know that the jets are born magnetically dominated. So they born magnetically dominated, at some point they become kinetically dominated, but we need powerful mechanisms in order to convert efficiently magnetic dominated into magnetic energy into kinetic energy. And one of these processes might be reconnection. A natural way to produce reconnection in these magnetically dominated relativistic jets near the source could be through producing current-driven kink instabilities. What is this? Okay, if we have a magnetized jet with a helical magnetic field with the strong toroidal fields, so it will be susceptible to this current-driven kink instability. And this might be a natural way to produce fast reconnection induced by this instability and turbulent reconnection. And then if we have fast turbulent reconnection, we might have all these processes that have been proposed, for instance, by Jan and Zhang in GRBs, and also by Janusz in relativistic blazars. And we could also explain, naturally, the simultaneous neutrino and gamma ray emissions in this TSX blazar. Okay, so how does the current-driven kink instability works? This is now in solar plasmas and in tokamak in laboratory experiments, but the idea is that if the system, let's consider a column, you know, a column of plasma that can be a jet with the strong toroidal fields. If we kick laterally this column, because with this kick we cause an unbalancing between the tension forces in this size that will be bigger than the tension, magnetic tension force in this size, and this will further detach or displace the column density from its equilibrium, so that this will increase further the distortion, right? And eventually this distortion will cause large helical motions that can even break our column, right? So this is the aim, or the heart of the current-driven kink instability. But if we have these distortions in the magnetic field lines, we may also have magnetic reconnection. So for instance, this process has been directly tested, reconnection driven by kink instability in a plasma column in the laboratory. And in the cross-section, we can see, for instance, the events of reconnection. And they found out that actually reconnection is very patchy and in space and bursting in time. So it is allows for flaring process. This, by the way, has been developed in an experiment in a plasma laboratory in UCLA University by these people. Okay, so let's move on. What about simulations? Here we have three-dimensional magnetohydrodynamical simulations of relativistic jets that we have performed with Mizuno and Singhi, and currently also with the help of my student Tania Torrejon and Kadovaki, so all these people. But what we see here is that we have perturbed this initially helical magnetic field structure in our tower jet, and then it ends up that with this perturbation, we perturbed with the precession perturbation. Because we have this strong helical toroidal component in our helical field, it gets unstable, and the kink instability actually develops and propagates downstream in the jet. So we do see, for instance, the kink instability acting in this place. And what we find that as time goes by, when the instability gets to its maximum linear growth, we have a decrease of magnetic energy, and at the same time an increase of the kinetic energy of the plasma, right? So we have this exchange, this efficient conversion of magnetic into kinetic energy. But what about the reconnection process that are taking place? So we did, as Luis has described in his talk yesterday, we did apply that, that algorithm that he described yesterday in order to search for the reconnection sites, fast reconnection sites within the simulation. And we see that once the instability gets its maximum, we have this, you know, this flaring process with reconnection increasing, and then it slows down afterwards. And if you see these points, these reddish, these red circles are the sites where reconnection is speeding up, was getting fast. So, and we end up with reconnection velocities around, in the peak, around 0.1 or so, and in the average values 0.05, which are pretty fast. And it's interesting to note that this speed up in the reconnection velocity, so what we might say, okay, we have a flare process here, occurs exactly when we have this maximum growth of the nonlinear growth of the kink instability. Where most of the magnetic energy is converted into kinetic energy. So the work, the process seems to work pretty nicely, right? It's a natural way to produce fast reconnection in these, and to get rid of the excess of magnetic energy, right? But also, and we see also that in these regions where reconnection is biggest, we get that the sigma parameter, that is the magnetization parameter of the relativistic plasma, gets minimum when we have maximum reconnection. So we have this magnetization of the process, of the flow, of the plasma flow. Okay. But these sites are also interesting for particle acceleration with the mechanism first order, the Fermi process that I have just described. So what we did in situ particle acceleration tests, launching test particles within these reconnection sites in these jets. And what we got was, this is a work in progress with my student, and we got this increase in the kinetic energy of the particles as a function of time, we do see again that exponential increase that we saw in our high resolution tests in localized current sheets that I showed before. And what we found is that particles with this energy are accelerated pretty fast to energies up to ultra high energy values, 10 to 17, 10 to 19 electron volts at sub-parsec distance scales for magnetic fields embedded in these plasma, in these relativistic jets between 0.13 and 13 Gauss. So these might be, these cosmic rays should have enough energy to produce both gamma rays and neutrinos. Okay, let's move on. It's enough about relativistic jets. In the final part of my talk, I would like also to stress the potential role of magnetic reconnection acceleration in the surroundings of the black hole. So in the core region itself, below, a little bit below the jet launching region, right? Is that possible? Okay, this may solve a long-standing problem. What problem? So, again, let's go to the observations. We know that most of the gamma ray emitters, extragalactic gamma ray emitters in the universe are blazar jets, or in other words, relativistic jets that point to the line of sight, and the emission is, artificially, not artificially, but boosted by Doppler boosting, right? So we see high luminosity, high emission because of the Doppler boosting. Nevertheless, more recently, it has been observed at TV's energies also non-blazar jets, non-blazar sources like Sena, Perseus, all these 6 sources so far. So these are radio galaxies, right? Essentially, their jets do not point to the line of sight. And then, okay, but for instance, has observed in Sena, Centaurus A, we know this blurred emission by Hess at TV's energies, and we don't know if it comes from the core, from the jet, from the nuclear jet. We don't know, because the resolution, the precision, cannot localize the region, right, with the current resolution of the gamma ray telescopes. So, we don't know if the emission comes from core or from the jet. Also, some of these sources show high variability emission, which means that the emission region is really compact. So if it's compact, maybe it's core or it's localized in the jet, but it's a compacted region. We don't know. But if it comes from the core, and because we expect the core to be magnetized in order to produce jets, etc., right? This community believes that these core regions are magnetized. So reconnection acceleration, if this is the case, if the emission comes from the core, reconnection acceleration could prevail. And there is another observational motivation for studying core process. And this comes in this diagram. In this diagram that we produced with Luis, we plotted essentially the luminosity as a function of mass of sources for almost 300 sources. This diagram includes both the core radio emission of known sources and the gamma ray power of these sources when these are observed between GVs and TVs, right? So we included all these emissions for these sources, and here we have both. We have non-blazars, we have galactic black hole binary systems. It's a pity that, yeah, I see that Felix, I think he's gone. Yeah, but anyways, we have galactic black hole binary systems here as well. And also we have blazars and GRBs. So in this diagram, we see essentially 2 trends. One trend that puts together blazars and GRBs, right? Here only the gamma ray emission of these sources. And we know that both cases, they have relativistic jets that point to the line of sight, so they are all blazar-likes. So we know that the emission is expected to come from the jet, right? But what about these non-blazars and galactic black hole binaries? The fact that they do not correlate in this diagram may suggest that they are their emission, their gamma emission, is produced somewhere else, not in the same place, right? Might be. It's another acceleration zone, another acceleration mechanism, right? And this motivated us to explore a core mechanism, a core process like this. So in this toy model, our idea here was to produce, to accelerate particles, to have the power to accelerate particles by reconnection in the surroundings of black holes, where the magnetic field lines coming from the accretion disk would find those anchored into the black hole and reconnect in the presence of a fast reconnection process, like for instance with underlying turbulence, a turbulent component that goes together with the large scale component of magnetic fields. This process could work quite well in geometrically thin accretion disks and also in ADAF-like accretion disks. And why is that so? We found out that the process actually works in both situations. And this because this process is essentially a coronal process that relies on the encounter of magnetic field lines in the corona that is associated to the accretion disk. So the details of the physics of the accretion process are not determining what happens for reconnection, although we do need, there is a dependence on the accretion rate. But with the fiducial parameters in both processes, we end up with enough power produced by magnetic reconnection in the inner region between the lines coming from the black hole, anchored into the black hole, and those that are anchored in the underlying accreting flow, right? But do we have enough fiducial evidence for reconnection in the surroundings of black holes? Okay, again, with numerical simulations, we do see, and yesterday, Luis has described these global numerical general relativistic MHD simulations that we are performing with Athena, both in global simulations and in shear box simulations. We have seen reconnection, turbulent reconnection driven by MRI, magnetorotational instability, and Parker Rayleigh-Taylor instability, right? And then we do see, applying the algorithm that Luis described yesterday, we do see the formation of these fast reconnection sites that here are marked with these dots, black dots and white dots, right, in the method that Luis described yesterday. So we have sites of fast reconnection. And okay, we can trust that if these sites have some, these sites will be able to, in principle, accelerate particles, right? Okay, another evidence, okay, not another evidence, but out of this, as Luis has demonstrated yesterday, using the algorithm, we could determine the reconnection velocity in the surroundings of the black hole, and we get velocities that are pretty fast. So we do have fast reconnection in the surroundings of black hole in the coronal accretion area. And can we accelerate particles over there? I mean, we believe so, and I will discuss this in a minute. But I should mention that not only our group, but other groups have also performed GR-MHD simulations in the surroundings of black holes and detected reconnection, both in two-dimensional tests like this by Parfrey, Giannius, and collaborators, and also like Dexter, McKinney, Tchaikovsky, all these guys have already found out reconnection events. Okay, now let's go back to our toy model, and in order to calculate the reconnection power that we can extract after out of an event like this in the inner region. We can write analytically with this toy model, we can calculate the magnetic power as a function of the parameters of the accretion flow and the mass of the black hole. So we have m dot here is the accretion rate, and the parameters of the corona and the reconnection region. Because all these parameters have a strong dependence with the mass of the central black hole, we can build a diagram of this reconnection power as a function of the mass of the black hole. And then, if we do calculate this diagram, we end up for a fiducial parametric space, either if we have a thin Shakura-Sunaev accretion disk or MADAF, a magnetized ADAF accretion disk, we get something very similar. We get something like this. This shaded area traces the region that covers the magnetic reconnection power as a function of the mass of the black hole from stellar mass black holes up to 10 to supermassive 10 to 10 solar masses. And we do see that it fits quite well the trend that is covered by non-blazars and galactic mass black holes. So my interpretation of this is that perhaps this should mean that the acceleration that is producing the gamma rays associated to non-blazar jets and black hole binaries, these gamma rays, at least the very high ones, could be produced near the core region by reconnection, magnetic reconnection, right? So this was kind of an observational constraint that still puzzles us. We don't know if this is true. Is that, of course, this would be a necessary condition, but it's not a sufficient condition. We still have to see with this result if we can reproduce the observed spectral energy distributions for the sources that are implied here. Because, for instance, Centaurus A is sitting here, IC 310, Perseus, all the radio galaxies that I mentioned that produce TeVs are sitting in this diagram, in this part of the diagram, right? So it's a necessary condition, but not sufficient. In order to get the sufficient condition, we need to explain the CDs, the observed spectral energy distributions, like, for instance, Centaurus A. This is the observed CD. Can reconnection explain at least the highest part of this spectral energy distribution function? Okay, we can try analytical models, single zone models, as we did in here for CEN-A, but the problem is that these models are too dependent of a whole bunch, too many free parameters, and we do not deal completely well with the absorption by pair production of the gamma rays. We can do the same exercise with galactic black hole X-ray binaries as we did in here, but it's a single zone model full of free parameters. But we can do better, and currently this is what we are doing. I'm going, in the last few minutes of my talk, I will just explain this new method that we are applying for the first time very rapidly, because this is going to be the subject of the talk of Juan Carlos Ramirez Rodriguez, who will talk right after me. So this is a work in progress in collaboration with him and Rafael Alves Batista. So what we did in here, what we are doing, we are combining 3 different techniques in order to deal with the full emission and the gamma ray absorption pair as well, in fully treatment. So we start with the general relativistic MHD simulation of the accretion flow around the black hole, using, for instance, the harm code, but we can do the same with Athena. And with this, we get the gas density and magnetic field distribution in the surroundings of the black hole. Then we do post-processing radiative transfer using the GR-MHD code for probing the background photon field produced by leptons. So essentially we get the synchrotron inverse Compton emission distribution. Then at the end, we inject cosmic rays into this environment in order to interact with both the gas density, magnetic field, and the photon field. So with this interaction, we can do the cascading of these, we can follow the cascading, the full cascading of these protons, injected accelerated protons. Of course, we are injecting accelerated protons because we are proposing that these protons are being accelerated by magnetic reconnection, that we have already demonstrated that is there in these simulations, right? So we have fast reconnection. We believe that we can produce these cosmic rays, we inject them with a given power law spectrum, and then we follow their cascade and get their entire emission. So we have both leptonic and hadronic emission. And then we, so as an example, and this is going to be further stressed again by Juan Carlos in his talk, but just to show you, this is our GR-MHD simulation. Here we have the background density distribution after a while and the magnetic field distribution in the turbulent flow where we do have reconnection, fast reconnection. Then we have this gives the radiative transfer simulation that provided the leptonic photon field, inverse Compton and synchrotron field for different energies, for 4 different energies. And then we inject our cosmic rays into this domain. This is going to be our accelerating region, and then we study the emission all over this path. And then we end up with this spectral energy distribution that we compare with the observation. The observation is in black. The blue part here is the leptonic contribution, inverse Compton and synchrotron. And we see that the inverse Compton can reproduce the X-ray emission. And we have the means to reproduce the very high energy TeV gammas that are observed, choosing different values for the power law of the injected cosmic ray spectrum. The best solution is this one, K1.2, which is compatible with the observations, let's say with the expected from observations and also from the simulations, right? And essentially what is producing this part is the proton-proton interactions, interactions with the background protons of the background field, right? The background in the surrounds of the black hole. So this is very interesting because even we see a trend for an increase above TVs at PVs energies. So we might have some kind of prediction that CTA will be able to probe. We may have a pivotron here, right? But this, of course, is something that Juan Carlos will explore better in his talk. Let me just finish with the neutrinos, because if we can produce cosmic rays up to energies 10 to 17, 10 to 19, then we can explain both. We can produce gamma rays, right, and also the neutrinos. This was a simple analytical work that we did back 2 years ago with the Chiali, where we tried to produce the diffuse distribution of ice cube with an entire sample of low luminous AGNs within this redshift sample, right? And we can reproduce more or less, but this is a simple analytical calculation with this fully GR-MHD, with this fully GR-MHD, sorry, I'm left-handed, so I'm always struggling with this, you know, that's made for right-handed people. But okay, anyways, with this fully method that we are doing, GR-MHD combining with radiative transfer, leptonic radiative transfer and cosmic ray cascading simulations to get the hadronic contribution, we end up with this neutrino emission for Centaurus A contribution, because this example that I gave you was to explain the Centaurus A emission, right? So this is, as I said, preliminary, but it's, you know, it's stimulating because I think this is the beginning of something that, you know, we can constrain better the parametric space, combining all these techniques together. So let me summarize the main results, the highlights of what I have discussed at least. In magnetized plasmas, particles can be accelerated by fast magnetic reconnection, driven, for instance, by the underlying turbulence in a first-order Fermi, producing power law spectrum distribution for particles that is compatible with observations, and we produced this both in PIC and MHD simulations. Reconnection acceleration may be important in blazar jets, as it seems to be able to produce cosmic rays with energies up to 10 to 17 or even larger. This, it may explain flare gamma ray emission and neutrino in magnetically dominated regions of blazars. Perhaps this source, this has to be studied yet. We did not with the reconnection model. Magnetic reconnection power can explain the gamma ray of black hole binaries and low luminous AGNs, non-blazar sources, as potentially, possibly, who knows, coming from near the core of these sources. The reconnection power at least matches quite well with the observed correlation of gamma ray luminosity versus black hole mass of both black hole binaries and low luminous AGNs over 10 orders of magnitude in mass. So this correlation through not it's a necessary condition that we found out, right, of this correlation with this nuclear, this core process would be something stimulating at least to search more. Reconnection accelerated cosmic rays in the surroundings of low luminous AGNs and black hole binaries are able to produce TV gammas that are not entirely absorbed by pair production, and is able also to produce neutrinos. And as I mentioned before, this will be further stressed in the next talk by Juan Carlos Ramirez Rodriguez. And finally, reconnection is an important in accretion jet systems, can be very important for particle acceleration, the dissipation of magnetic energy, and conversion into kinetic energy. Last but not least, I'd like to mention that our group is working, our group and actually the entire CTA collaboration is working very hard in the efforts, in the participation of the CTA, and also in the construction of the precursor of the CTA that will be the first part of the CTA that will be installed in the south site in Chile. That is going to be the ASTRI mini array. That is, you know, it's an array of 9 telescopes that we are building in collaboration with the Italians, and this will be the deployment will start next year. So we will be able to do Pevatron science already in 1 year or so with the first telescopes that will be installed, and we will be participating directly in this effort. Thank you.